Um, hmm, it worked earlier. I am not able to share the screen. Well, I'll try. Can you see the screen? You're able to see the screen?
Yes.
Okay, yeah, right. Thank you. Yes. So good morning, good afternoon, and good evening, depending on where you are. It's a great pleasure and privilege to have this opportunity to give this keynote address. And I actually thank the organizers, Hugh and Vladislav in particular, for inviting me. First, there's an old saying in my language that what we have learned is equivalent to the size of the earth that we can hold in our hands, size of the fist. But what we have yet to learn is about the size of the earth itself. So I'm only here to share my own understanding of methods of solving vibration problems. And some of these are based on well-established knowledge, but there may be others which are based on my own understanding. And it's possible that my understanding is not complete, and there could be rooms for improvement. There could be errors, mistakes. So feel free to challenge and correct me if you find anything not that convincing. So this is an obvious question, but it's easy to address. So let's address it first. Software packages such as ANSYS, Abacus, or Nastran, any of these packages based on finite elements are quite easy to solve, and they can actually handle vibration problems. You can calculate the natural frequencies and modes quite easily. But it's not easy to gain physical insights into the behavior of vibratory systems using such packages, particularly obtaining parametric solutions is a lot easier with analytical methods. And also, analytical methods are easier to generate benchmark results. So that's why you will see that in journals, including sound and vibration, there are numerous papers that deal with development of analytical methods. They continue to appear, and also when you look at the papers dealing with vibratory behavior of systems, again you find often they use analytical results as benchmarks. So of the analytical methods, we will be dealing generally with three commonly used analytical methods. There is a particular order in which I have listed them, and there is a reason for this preference, and I will let you know why. So my first preference, where possible, is the so-called dynamic stiffness method, where you have exact solution to the governing partial differential equation as well as any boundary conditions. Secondly comes what is called Gorman superposition method, which I think is the next best method. And then you have a number of variational methods such as the Rayleigh-Ritz method and the Galerkin method. So we will be dealing with basically these three methods, and there are some variations within them. For example, with the Rayleigh-Ritz method, we can also use Lagrangian multiplier or penalty functions to enforce constraints. So then we have a question, how do we know when a solution is not exact? I think it's easy to appreciate that no other solution can be more exact if we have an exact solution. So that means if a solution can be improved in some way or other, it cannot be exact. So if a solution depends, for example, on the matrix size, it's not going to be exact. The reason I raised this is I have seen in manuscripts submitted for consideration as a reviewer, mostly, I've seen papers which claimed to present exact results, but they were really series solutions where the accuracy of the solution depended on the matrix size. So there is some misunderstanding about the exact method versus accurate analytical method. So what is an exact method? So the solution must satisfy the partial differential equation everywhere within the domain. So it has to satisfy exactly, not approximately. Then the boundary conditions also must be satisfied exactly everywhere in the boundary domain. So usually a closed form frequency equation is found, and the roots of this so-called frequency equation then yields all modes and frequencies, not just one or two modes and frequencies, but using the same equation, one should be able to derive all the natural frequencies and modes, and for continuous systems, there are infinite number of modes and frequencies. So it's possible that the calculation of roots may involve some approximation, maybe truncation. For example, if you look for solution of sine lambda is equal to 0, we know that it is pi, and pi can be calculated to any desired accuracy for all practical purposes. It's only limited by machine precision. And it's OK to call it an exact method. Otherwise, we won't have any exact method at all. So the first method, my favorite one, is the exact dynamic stiffness method, where you write the equations of motion for various points on a structure. If you take a framed structure, we would be looking at the equilibrium, the dynamic equilibrium at the joints or the nodes, and you would write the force and moment in terms of either translation or displacement at those nodes. So you will have a dynamic stiffness matrix. So that matrix, the coefficients of that matrix actually includes the effect of both the elasticity and the distributed mass. These coefficients were once called dynamic stability functions. And if time permits, I will briefly explain the history behind that. So these equations, you have a set of equations in terms of the dynamic stiffness coefficients. And if you are looking for natural frequencies and modes, you have on the right hand side of the equation 0. On the left hand side, you have the dynamic stiffness coefficients matrix times a vector of unknown nodal displacements, which could be translations or rotations. That's talking about a frame, a skeletal frame, but there is equivalent dynamic stiffness matrix for plates and some kind of shells as well. So then the natural frequencies are obtained by setting the determinant of the dynamic stiffness coefficients to, the dynamic stiffness matrix to 0, and that determinantal equation is what we call the frequency equation, and the frequency equation will have infinite number of roots. And there is a nice algorithm called WW algorithm, which is ideal for finding these roots. Now the algorithm is named after the two co-inventors, Whitrick and William. Both have sadly passed away. Professor William, who was at Cardiff, and I have worked together on 2 projects, and we have co-published papers. And he was one of the co-inventors of this algorithm, which nicely enables the calculation of the roots of the frequency equation. Is everybody able to hear me? Okay, good. So let's look at the application of the dynamic stiffness matrix, which I denote as, dynamic stiffness method, which I denote as DSM. If you consider the vibration of a very simple frame, an A-frame which is pinned at the base, the first vibration mode would look like what I have sketched there. In fact, you can show that these will be 2 half-sine waves. So they are pinned at the base and rigidly connected at the apex at the top, and this is how the vibration mode looks like. The first vibration mode would look like. So the way the dynamic stiffness matrix works is you express the forces or moments. In this case, because the frame cannot sway, we are not interested in the force, so we have a moment equation. The moment coming from the first member on the left plus the moment coming on the second from the second member, K1 S1 double prime theta 1 plus K2 S2 double prime theta 1. Sorry for using these symbols. These double primes indicates that these are stiffness coefficients which are modified to take into account of the fact that one end of the beam is actually pinned. If it wasn't pinned at the base, we will not have a double prime there. It's just an accepted symbol. And K is simply EI over L. So in a static case, the S1 double prime and S2 double prime will be equal to 4. 4 EI over L is the rotational stiffness. And they both share the same rotation because it's rigidly jointed at the frame. So you have the equation of motion shown at the top, and if you have a symmetrical frame, both K's will be equal and S will be equal, and that gives you the frequency equation as Ks theta is equal to 0, and for non-trivial solution, theta is non-zero, therefore Ks is 0, K can't be 0, so S is 0, and sorry, S double prime, and that's actually in this case sine of lambda, which is a frequency parameter, and that enables us to calculate the natural frequencies of this frame, which happens to be equal to natural frequencies of two simply supported beams there because of the similarity of mode shape. So you can see this is an exact solution, and for other structures we can write similar equations. It may not be as straightforward as this, but you get a transcendental determinantal equation, the solution of which can be easily found using the WW algorithm. Okay, so it's applicable for skeletal structures and also some plate systems. And you can use the WW algorithm, as I said, to find roots. Okay, so as I said earlier, one can argue about the accuracy of evaluating pi, but the solution does not require further changes to the method itself, and the frequencies can be calculated simply using that frequency equation. Sine lambda is equal to 0, or whatever the transcendental determinantal equation is. So the method in this case is exact. Okay, so unfortunately, exact solution is not always possible. So let's look at what I regard as the second best for continuous systems. So here you see a plate which is simply supported along two edges. The dotted lines show simple support and the other two edges are free. So it's a simply supported free plate, which I denote as SSFF plate. So edge 1 and edge 2 are free, but the other two are simply supported. And there is no exact solution to this problem. To have an exact solution, the Levy type, you need to have at least two opposite sides simply supported, or what they call gliding, which means shear free at both ends, but the slope is constrained. So those are the two possible conditions that would enable you to get the natural frequencies and modes exactly. So in this case, there is a nice method called Gorman superposition method. The person who developed this method, Professor Danny Gorman, sadly he passed away a few years ago, and we used to meet at a number of conferences, and he nicely explained this method. And the first time I learned this method was at a conference when he explained it, and I actually liked it. Okay, so how does it work? So the idea is you find the solution to the actual problem by composing the solution from two, in this case, two building blocks, but there can be more than two building blocks in some cases. So the building block 1, what you see up on the right top there, has got three simply supported edges The dotted lines are three simply supported edges. So in this case, we have two opposite sides simply supported, which means we can actually find exact solution to either forced or free vibration problem. Then the clever thing that Professor Gorman did was to find the forced vibration solution to the plate, the building block 1, subjected to some edge loading along the free edge. Now it can be a loading, or it can be, well, it can be a force, or it can be a displacement. You can choose either. So you apply a distributed force there, and then you find the response. The forces will be harmonic forces at unspecified, undetermined frequency omega. Okay, so we are getting the solution, but assuming different modes in the x direction. So with the simply supported edges, you can have 1/2 sine wave, 2/2 sine waves, 3, and so on. So for a number of these sine waves, assuming that particular shape in the x direction, we then find the forced response. And likewise, we look at building block 2, where we now have two opposite edges simply supported parallel to x-axis, and now the force, the distributed force, is applied along edge 2, whereas earlier it was applied along edge 1. And then the idea is to combine these two. Okay, so we combine a series of forced vibration solution with unknown distributed loads along the boundary at unknown frequency. Okay, so we add them together. So we superimpose the solution and then say the final solution must satisfy the edge conditions along edge 1 and edge 2, which are namely there should be no force. Okay, and that is satisfied approximately by multiplying by the corresponding mode functions, which are sine pi x over L or sine pi y over L or whatever. Okay, so you have a weighted average solution based on the building block response to unknown edge loading, but we then say the edge loading must be such that the boundary forces along edge 1 and 2 should be 0. So this then gives rise to a homogeneous set of equations. So once again, you have an eigenvalue problem. This time, the size of the matrix depends on the number of terms you choose for the displacements in the x direction for building block 1 and the displacement in the y direction for building block 2. Okay, so with that matrix size, you have a determinantal equation, and when you solve it, the unknown frequencies actually will give you the natural frequency of the original system. And that's because we are satisfying, it's important to note that we are actually satisfying the governing differential equation exactly, because both building block solutions satisfy the governing differential equation exactly because they are Levy type exact solutions. What is not being satisfied exactly is the boundary condition, or the boundary conditions in this case. The boundary conditions are being satisfied approximately through a series, but the overall solution of the domain of the plate satisfy the equation of motion exactly. And the reason why I like this method is exactly that. From my experience, I found the Gorman superposition method converges a lot faster than the Rayleigh-Ritz method, because in the Rayleigh-Ritz method, you actually have to satisfy the equation of motion effectively when you minimize the so-called energy functional. What you effectively do is you satisfy the governing differential equation, and that takes that seems to take longer because you have to work on the entire area, whereas for this method, you just have to work along the boundaries. Okay, so I think that is a clever trick, and that's why I like this one as the second best. Okay, so you can use, as I said, you can use exact solutions. In some cases where exact solution is not available for the building blocks, you can still use approximate solutions. And one of my former PhD students, currently a colleague at Waikato, Dr. Yusuke Mochida, his PhD thesis was based on developing the superposition solution using approximate Rayleigh-Ritz method to find the modes of shells, which is not possible to find using the exact method. And then he used the superposition method. So it's a combination of Rayleigh-Ritz and superposition, and that was a little bit faster than using the Rayleigh-Ritz method alone. And the reason for that is you first find the approximate solution for the building blocks as accurately as you want, and thereafter you deal with the boundary condition. So you tackle one problem at a time, and that may be the reason why it worked more efficiently, or the convergence appeared to be faster. Okay, so yes, the boundary equations are formed with weighting functions in the form of modes of building blocks, which are often exact but not always. So you can use approximate solutions as well. Okay, so the number of equations we have is equal to the number of modes. And again, this solution is approximate because as you increase the number of terms in the series for the building block solutions, then the accuracy is going to improve. And this is one of the areas where I have had disagreements with some colleagues on whether this can be called exact or approximate. The building block solutions, I agree, are exact, but the final solution, it's an excellent method. It converges very fast. It is still only approximate. Okay. So some of the problems, we can find the solution in a bounded way. So we will actually know whether the solution is an upper bound or lower bound. And that sometimes is quite useful, because if you find the upper bound using one method and lower bound using another method, you can pretty much bracket the solution as practically as possible close to the solution. And you can also estimate the maximum possible error. Okay, so we will, time permitting, we will deal with the boundedness later. Okay, so let's just compare the dynamic stiffness method and the Gorman superposition method before going into the next one, which is Rayleigh-Ritz method. So the governing differential equations are already satisfied in both cases, but and the frequency equation is a determinant of a boundary or continuity condition matrix for GSM. So for DSM, the boundary conditions are exact, applicable for skeletal frames and some plates. Sorry, the second statement I mentioned, the frequency equation is a determinant of a boundary condition or continuity condition matrix, applies to both DSM and GSM. But for GSM, it is approximate. Okay, so it's the boundary conditions are expressed as a series solution, and it's applicable for plates and shells and most likely some solids, but I haven't actually looked at those in detail, so I can't be 100% certain that it is true for solids. Okay, so DSM is exact, GSM is approximate, but it's very good because it only has to work along the boundary, not the entire domain of the continuous system. So then we turn to the variational methods, and the most popular one I think is the Rayleigh-Ritz method. And there we minimize a functional which is really a ratio of the potential energy over a kinetic energy function without the frequency appearing in it. So in this method, the original form of the Rayleigh-Ritz method, assumed displacement forms must satisfy essential boundary conditions, which are also called geometric boundary conditions. The idea is when one minimizes the functional, you get the best possible solution, and one does not need to worry about the natural boundary conditions. In other words, if you have a free boundary of a plate, then you don't need to worry about satisfying the free boundary condition. You only have to satisfy conditions where a geometry is constrained, whether the displacement is 0 or translation or rotation is 0. You have to satisfy those, but not force or moment being equal to 0. The minimization process ensures that it is done. It's a point sometimes missed by some researchers where they try to find functions which also satisfy the natural boundary conditions, but in trying to do that, they may be actually missing out on other functions which could converge faster, and therefore those solutions are not necessarily any more accurate than the solutions which do not necessarily satisfy the natural boundary conditions individually, but as a series they will be forced to satisfy through the minimization process approximately. Galerkin's method is similar, but here well, you minimize the weighted residual error of governing partial differential equations, but also any residual forces on free boundaries. So the Rayleigh-Ritz method automatically forces the function to go to the lowest possible potential energy form where the edges are free, whereas in this case that is not happening. So therefore you have to have an extra term to make sure that the residual forces along the edges or moments along the edges are also minimized. And here again, the assumed displacement forms must satisfy essential boundary conditions. For obvious reasons, I prefer the Rayleigh-Ritz method because one doesn't have to worry about natural boundary conditions. A couple of things to mention here. So people have worked for a long time on finding the best polynomials. Professor Batt and others have worked on orthogonal polynomials, and there's also the type of Fourier series method called whole element method. Now then the question arises, do we need to strictly use admissible function? And interestingly, the answer is no, and I will explain that shortly. So the boundary conditions can be enforced. The essential boundary conditions, the geometry conditions, can be enforced using approximate methods such as the Lagrangian multiplier method or the penalty method, and that's what I'm going to spend some time on next. Okay, so just to recap, the Rayleigh-Ritz method requires, the original form requires each of the admissible function to satisfy the essential condition, but we are going to bypass that requirement. Okay, so let's just take a moment to look at the origin of the Rayleigh-Ritz method. Now this there has been some debate over whether it should be called the Ritz method or the Rayleigh-Ritz method, and Professor Art Lisa and I have discussed this over many conferences, and we didn't come to an agreement on this. We agreed on the origins of it, but whether it should be named the Ritz method or the Rayleigh-Ritz method, unfortunately we could not agree on that. I believe it should be called the Rayleigh-Ritz method. And the reason, one good reason, is a contemporary of both Rayleigh and Ritz, Courant, has actually mentioned in his paper that this method was independently conceived by both Rayleigh and Ritz. And the Rayleigh's paper, Rayleigh's book, The Theory of Sound, and other papers perhaps don't necessarily convey the idea as clearly as Ritz's paper, and perhaps Rayleigh has not developed it as conveniently as Ritz has in a form that is readily usable, but Rayleigh did give the idea of the minimization process, which can be inferred from his work in the book, The Theory of Sound. Okay, so I'm just going to give an example. So we have here a propped cantilever, and we want to find the natural frequencies, and we have zero zero translation, zero rotation at the left end, zero translation at the right end. And the method involves choosing functions which satisfy all these conditions. You can choose any function you like as long as these conditions are met, and then assemble them, put them into the energy expression and minimize. You will then get the best combination, which hopefully is very close to the natural frequency and the natural frequencies and the modes. So if you use three functions, you will get three frequencies, and these are upper bounds to the actual frequencies. But it's not easy to find, just checking the time, it's not easy to find functions that satisfy all the constraints. So it would be nice to be able to remove some of the requirements. So let's demonstrate what happens when we remove one of the constraints. And this idea was proposed by Courant in a paper in 1943. I will leave some interesting references as a part of this presentation at the end, which people may be interested in reading. And this is such a seminal paper. It's got ideas which still I think could be explored further. Right. So what he said was, okay, let's replace that support with a spring support. And it was later known as artificial springs. So with the spring, there was some restriction. Then what you do is you make sure that the spring stiffness is very high, so it more or less gives you the required solution. So you can then not worry about the essential condition that the displacement at the right end should be zero, but add an extra energy term with an artificial stiffness with K being very large. You can do that with all three constraints, and then you can choose any function in the universe you want as long as it's continuous. Then you can put that into the solution, and then you need to put three different springs and enforce the boundary conditions. See what happens. There is no spring at all. There are three frequencies. Put some spring stiffness there. They are going to increase, keep on increasing. You will see that these frequencies will get capped because you can never pass infinity. So the spring stiffness has to be lower than infinity. So they will asymptotically approach the constraint solution from below. Now there is a problem. Rayleigh-Ritz method gives an upper bound. Here we are looking at the upper bound of a lower bound model. So that is something that that problem needs to be addressed. It has been addressed now, but that was one of the criticisms. Okay, so and the other criticism was, this was noted by Sinniah back in '74, that one doesn't know how much error is there due to the violation of, this is called the penalty method, violation of the constraint condition, because although it is a rigid spring or stiff spring, there may still be some movement. So what's the solution? Okay, the solution that I came up with is to use negative stiffness and track the frequencies from both directions. So what you find is when you use negative stiffness, you will find an upper bound of the upper bound, and the solution that lies between a model with a positive stiffness and a model with a negative stiffness will give you the right answer. So you can actually estimate the error if you choose one positive stiffness and one negative stiffness. One will be below the true frequency and the other one will be above the frequency. And you can see, I don't know whether you can see the mouse. So you see at this end, the calculator, can you see the mouse? The frequency is lower. Here the frequency is higher. So it must lie between there and there, so we can bracket it. Okay, so major criticism is resolved. And how did we get there? There's an interesting story, and I will try and tell you before I finish. So it all starts with using a mass. So let's see what happens when you use a mass. Okay, with a mass, increase in mass decreases the frequency, so you can actually asymptotically approach a constrained solution by also using mass. But this time you actually approach it from above. So using mass will give an upper bound solution to an upper bound model. It will be a true upper bound. And you can also use negative mass, and when you do that, you will get this. And what happened was I made a mistake in my PhD thesis where in modeling a plate like this, I was looking at the post-buckled solution of a plate and the vibration in the post-buckled position. And I wanted to allow for the movement of the loading head, the mass of the loading head. And I took that into account through an energy term. But instead of positive mass, I had effectively put in a negative mass. And it was a few years later, one of my final year undergraduate students spotted the mistake when he was trying to model a beam. I told him to be careful with the free body diagram and make sure that the signs are correct. He followed my advice and he came back and told me my thesis had the wrong sign. And I thought it was just a careless typo, but I found I have to confess, I typed the thesis by looking at my Fortran program. So the problem was there originally in my Fortran program, and it worried me because we had excellent agreement between theory and experiment, and I also knew that the mass made a difference. And after sweating, I reran the program with the correct sign of mass. To my surprise, I got very similar results, and I was stunned. I didn't expect that, because I knew that the mass had an effect, and then I realized the mass was so high that it was practically constraining it. So that's how I discovered this, and it fortunately led to a number of papers, including a theorem on how you can use positive and negative mass to model these systems. So sometimes it's good to make mistakes. And I just want to show you another thing about using mass versus using stiffness. With the mass, what you find is, so I should wind up soon. What you find is that the higher frequencies converge faster. Sorry, the higher modes, the frequencies of the higher modes converge faster. And that is because the restraining force, the constraint force, comes from m omega squared times displacement. So the higher the omega, the higher the restraining force. So if you use stiffness type penalty, while they may work well for lower modes, for higher modes, you may want to consider using mass, which works a lot better. So I have to finish soon. So I was going to touch on the boundedness, but because we are running out of time, I'll just mention the Lagrangian multiplier method can also be used to enforce constraints, and the Lagrangian multiplier method has actually been used to generate both upper bound and lower bound solution to a plate problem, and that was a buckling problem of a plate. And that was in 1946 by Budiansky and Hu. That is in a NACA report, the previous version of NASA. And this is freely available. Anybody interested? It's a very nice paper to read. So you can use the same formulation to get upper bound and lower bound solution. And the way it works is if you consider functions giving exact results for a less constrained system, for example, using sine functions for simply supported plates or cosine functions for gliding plates, they can be used with boundary conditions as constraints. So you then start with those less constrained functions and you approach the higher constraint solution. And when you do that, you will get a lower bound. Okay, so there are some references at the end of this presentation, and if anybody is interested, you could actually refer to those if you are interested in finding how to get the bounded solution. It is always nice to know when you have an upper bound solution. It is nice to know what the lower bound is, if at all possible. So briefly, these are the conclusions. DSM is exact, GMS is next best because you only need to worry about the boundary. Rayleigh's method is good and it's versatile, convenient, and you don't need to worry about the geometric conditions. You can use a penalty method, and you can use negative stiffness and positive stiffness, or positive mass and negative mass, and you can then calculate the effect of the constraint violation and control that error by choosing the appropriate magnitude. Okay, so and where available, bounded solutions will help to address the lack of exact solution. I think that's probably a good point to finish, and here are the references which I will leave with the organizers, and if anybody wants, they can get a copy of the presentation. So, yes. Any questions?
Thank you very much. Very interesting presentation. So actually it reminded me some of the presentations that I